Hello dear students, I am Priya Kulkarni from Civil Engineering Department of Parvatibai Genba Mozi College of Engineering, Wagholi, Pune. In this session, we are going to start with the numerical of beam with the both ends hinged or simply supported beam, a continuous simply supported beam. Okay, so before starting before starting this numerical, we are going to recall some things that we are going to form a flexibility matrix. This is the main highlighting part of the flexibility matrix method. Okay, and for forming that uh, met, flexibility matrix, we have to follow or we have to first make the structure make the indeterminate structure a released structure. Okay, we are going to release the unknowns, and by using this concept we are going to form that flexibility matrix. Okay, this is the basic criteria or basic assumption that we are going to made in this method. Okay, and also we are going to form a flexibility matrix that is a square matrix. Okay, and it is a symmetrical matrix. Okay, we are going to form a flexibility matrix, square matrix, and this flexibility matrix is a symmetrical matrix. Obviously, or this is the check for in the exam that we are in the right track or not, that whatever the flexibility coefficient that we have found, uh, and the diagonal coefficient, that is diagonal coefficient, okay, moving from left to right, okay, those coefficient have to be symmetrical. Okay, this is the check. And also the cross coefficients means the coefficients except the diagonal coefficient, those are called as cross coefficient, and those cross coefficients have to be value positive or negative, it depend, and this the value of this cross coefficient also varies, these are not symmetrical. Okay, so this is the basic criteria, and we are going to start with this numerical. Okay, so analyze the continuous beam using flexibility matrix method and draw bending moment diagram. This is the numerical that has to be asked, that was asked in the exam, and this question was asked for 10 marks. Okay, all the means if you have if they ask complete numerical, that is analyze the whole beam and draw bending moment diagram, this it means that question is for maximum marks of 10. Okay, and if suppose they are supposed to ask one theory question of 4 marks or 2 marks, and the remaining marks question, the total marks for one question for at a time is 10 marks. Okay, so if suppose in the exam they will ask 2 marks or 4 marks theory, and the remaining 6 or 8 marks numerical, so in that numerical we just have to form or we just have to solve up to the flexibility matrix, we don't need to solve up to the bending moment diagram part. Okay, so they will ask directly in the question that the solve up to this part. Okay, so we'll start. It is a continuous beam, two span continuous beam having spans AB and BC. AB span is loaded with a 30 kilonewton load, and this 30 kilonewton load is eccentric, that is 2 meter and 4 meter is the distribution of the span. And then BC span is loaded with two loads, one is point load exactly at the center, sorry, not that point load, it is loaded with a UDL of 10 kilonewton per meter, and whatever I have shown here is the point load that I have converted for the uh, notation purpose I have shown with the help of arrow. Okay, so it is actually one UDL only. Okay, the first step is finding the degree of static indeterminacy. Okay, in the very first step we are going to calculate the degree of static indeterminacy, and according to that we are going to select the redundants. Okay, and this is the basic step, simple step we are going to do in all the 4 units of our SA2 subject. Okay, the first step. So degree of static indeterminacy is equals to number of reactions minus number of known equations. Okay, so number of, while finding the number of reactions we are going to neglect the horizontal forces. Okay, we are going to totally neglect the horizontal forces, whatever. And also in the number of known reactions, that is what are the number of known reactions or number of known equations, that is summation of moment is equals to 0, summation of horizontal forces is equals to 0, and summation of vertical forces is equals to 0. So these are the three basic equations of equilibrium. But here in the case of beams we generally neglect the horizontal or axial force. Okay, that's why what are the our known reaction, we are going to neglect the summation of fx is equals to 0. So number of known reactions in this case by considering or by neglecting the horizontal loading is 2. Okay, similarly in the reaction part or in the unknown part, there also we are going to neglect the horizontal or axial forces. Okay, so if we are, or also if you have one you have confusion regarding where to take the unknowns, means where to take the horizontal force or not, you just simply follow the basic rule, that is number of known reactions 3 and whatever the unknowns in the given structure. Okay, you can go by two way. If we are going to neglect in R part, that is number of unknown reactions, then you are supposed to neglect it in the number of number of equilibrium equations. Okay, then what are the number of unknown reactions? Unknown reactions, as this is a simply supported beam, there is not any movement or external movement due to support. Agree. Also there is not any hinge support given here. Okay, if they have given any hinge support, then we have two unknowns at the hinge. One is horizontal force and another one is vertical force. Okay, so that part is not given here. So simply the three vertical reactions are the unknown. So three vertical reactions are the unknown. Also, what are the number of equilibrium condition? Equilibrium condition by neglecting horizontal loading is summation of moment is equals to 0 and summation of vertical force is equals to 0. Okay, so these are the two basic equilibrium conditions for this case. Now we have degree of static indeterminacy is equals to 1. So that means we are supposed to consider only one redundant. Okay, and that redundant we can select at the end suppose. Okay, so for the betterment of solving or for simplification of numerical, we can assume RA is equals to redundant or RC as redundant. But again we have habit of, or for the simplification again we will consider from the right part, that is we will consider RC as a redundant. Okay, so it is denoted as R1, that is redundant 1 is equals to RC. So here we have only one redundant, and this one redundant is by degree of static indeterminacy. If we got two number of statical indeterminacy, then we have to select the redundant R1 and R2. Okay, now next step is forming the flexibility matrix. So for forming the flexibility matrix, we are supposed to draw the release structure diagram for the given condition and for the for to show the redundant code type. Okay, now draw release structure M diagram and M1 diagram. M diagram is the original loading diagram. M diagram, that is capital M diagram, is the original loading diagram, and M1 diagram is the redundant diagram. Now what is the redundant diagram? In the redundant diagram we don't show any of the load. Okay, here we don't show any load, we just only show the supports. Okay, we only show the support with the reactions, and if there is any fixed end then we will show there one movement and one vertical reaction. Okay, likewise, so in M1 diagram is only for redundant and the given support loading, given support reactions and movement if any, and M diagram is for the movement diagram for the real structure. Okay, for the original structure. So these are the two diagrams, these are very much important diagrams. Okay, so what I have done here for M diagram, I have shown all the loads and the span, and also I have calculated the reaction at B. Okay, so you can easily calculate the reaction at B for continuous beam, and this is very simple type, that is simply supported beams. Okay, and M1 diagram is for redundant diagram. Now what we have selected redundant, we have selected R1 as redundant, so we are going to apply unit force at that redundant. Okay, that's why RC is equals to 1. Okay, and these values will calculate in the next steps, and then we'll write here. Okay, if you don't know then just keep it blank. What we know up to this point, we know that we have selected R1, that is redundant, as RC, and where we have selected the redundant, there we are going to apply the unit force or unit movement if we have considered movement as the redundant. Okay, then moving to the next part, this is the table that we have to form. Okay, now just look at this table very carefully. First part is member, second is limit, third part is origin, fourth part is EI. So I forgot to mark one line over here, sorry. So EI and M is the original movement diagram, and small m1 is the movement diagram of redundant. Okay, so we have these two diagrams, and here we are going to cut the sections at particular spans like this. Okay, like this we are going to cut the sections and separate each span, and then we are going to find this capital M value, that is moment value. Okay, now just member CB, what are just moving from right to left, what are the movements coming and what are the limits and origin, that part we'll write it over here. Then member is, first member is CB. Okay, limit is 0 to 4, limit is what, here it is 0, and here the span, given span is 4 meter, that's why 0 to 4 is the limit for CB. And origin, we are going to start what we are going to calculate, or we are going to mark the distances with a reference to C. Okay, that's why C is our origin point. Okay, this origin point will differ from span to span. Okay, if we are going to consider the next span, then we are going to consider only up to that span, origin up to that span. Okay, we don't need to consider from the ends. Okay, for simplification only, if we are going to consider it from end, then we have to consider for all the remaining two members. Okay, that's why for our simplification and the time being, we will consider the each span separately and each origin according to starting point of the span. Then what is the capital M? Now here just we have considered this span CB, and we are going to cut the section and with a distance x. Okay, so this distance is x, that is unknown. So what is the load over here? It is a UDL of 10 into x. Okay, and it will act up to at a distance of x by 2. That's why minus 10 x square by 2. Why this minus came? Because this loading is downward side. Okay, and it will create a clockwise movement like this. Now here just look at the span. Okay, so this is the span and this is the UDL, and because of this UDL, this span will rotate like this. Okay, this rotation is in clockwise direction, and we have considered clockwise as positive, sorry, we have considered clockwise as negative, that's why it is minus. Okay, just we'll first write the M diagram part and then we'll go for M1 diagram, okay, for the simplification. Okay, then next span is BD, this B to D. Okay, wherever the loads are coming, point loads or uh, inclined loads or uniformly varying loads, wherever the span has the variation in terms of loading or in terms of EI. EI can be variable, but in this numerical we have the same EI, constant EI, but where the loading diagram change or where the EI change, that point we have to cut that, or we have to consider that part separately. Okay, now here span BD and the length or span is 4 meter, so we will consider here it is 0 and here it is 4. Okay, and what origin it is? The origin is B, because we have considered 0 over here. Now again I will explain. If we have considered for BD part, if we have considered C as origin, then we'll take the limit here, starting is 4 and here it is 8. So limit will be 4 to 8 like this. Okay, understood? So whatever the distances you are going to consider for the limit value, and whatever the origins that you are going to consider, just keep a uh, fine calculation at that point. Okay, just don't make any silly mistake. Any mistake over in this table, it will lead to something wrong. Okay, in the in the original value, okay, answer value, you will get marks for the steps, but it will be the lesser than out of out. Okay, okay, now next part is DA, member DA. Member DA has 2 meter span and will form the origin at D and the limit is 0 to 2. Okay, so we'll finish this part and we'll go for the calculation of M. EI is 1, same for or constant for both the spans. Okay, now here we are going to cut the section, at this BD span. Okay, span is BD and we are going to cut the section at the BD span. Now we are going to calculate whatever the loads or whatever the moments are coming from this end to this point. Okay, now distance here it is x. Okay, and this B to C distance is 4. That's why uh, we'll calculate the values in terms of x. Okay, now just look at here, it is 10 into 4. Okay, this UDL into 4 is the total distance and it will act at the center. Okay, so this is 2 meters. Okay, this is 2 meter and plus x. Okay, why x? Because we are calculating movement at this point. Okay, from C to this point. Okay, That's why it is x plus 2 plus 63.33 into x. What is 63? 63 is the reaction at this B, okay, RB into x. Okay, so this is the, and only this part or this much loads are coming on the way. Okay. Now for M diagram of DA span, okay, we'll cut the section over here and we will calculate all the loads up to A point. Okay, so minus 30 into x, so this 30 into x minus 10 into 4, this is this UDL 10 into total distance 4, it will converted into point load. Now plus into whatever the distance, now here it is the span, the span is 4 plus 4, it is 8, sorry I have done a mistake over here, it is 8, it is not 6 over here, it is 8. Okay, and plus x, x is the distance from D to the cut section. Okay, so this is the 8 value. Okay, and uh, for this reaction, it is 63.33, distance 4 plus x. Okay, so this is for this original loading diagram movements that we have calculated. Just only we have to cut the section and we have to calculate the movements from the ends. Okay, movement from one fixed end. Okay, so we have calculated all the loads from this C point. Now moving towards the small M1 diagram, that is for redundant diagram. Now here we are going to do the same thing for this redundant case, that we are going to cut the sections and we are going to calculate the loads or movements at that point. Now just consider this BC or CB span, origin is C, limit is 0 to 4, same will be applicable for this M1 diagram. Now what we have considered RC as redundant, that's why we have applied unit load at the C point. Okay, that's why this, and we have cut the section over here, so that's why we'll take the moment of RC, that is 1 into x, and why this is positive, this will create a movement of this nature, and this is anti-clockwise nature, and anti-clockwise we have considered positive. Okay, that's why here it will come 1 into x positive, only this much part will be there. Okay, now moving towards the BD span, we'll cut the section over here and we'll calculate the distance. Now 1 into 4 plus x, that is here x plus 4, okay, into, sorry, minus 1.66 kilonewton is the redundant, because of this 1.66 into x, this is the total distance, or this is the distance that we are considering over this cut section. Now in the next part, that is DA span, limit is 2 and origin is D, and we will consider all the distances from this point. Okay, so x plus 8, so this 4 plus 4 into x. Okay, so x plus 8 is the is for RC, that is 1 into x plus 8 minus 1.66 into 4 plus x. Okay, so this is the uh, movement configuration for M diagram and M1 diagram. Now moving towards the calculation of coefficients, that is displacement coefficients and flexibility coefficient. Now here displacement at redundant coefficient, this is very common step in all the numericals of flexibility matrix. So here we are going to determine the deformation in the indeterminate structure in the direction of redundant. Okay, so we are going to calculate this displacement dr1. So displacement at R1, R1 is the redundant RC, that C point that we have considered are redundant at 1. Okay, so that's why displacement at R1 dr1 is equals to integration of limit 0 to L capital M into small m1 divided by EI into dx. So all what we are going to do from this in these 2-3 steps, we are going to simply do the integration part and the putting the limit part and calculate and getting one value. Okay, so this maths part is here. So what we are going to consider, m into m1. Here we have calculated this m part and we are going to multiply with this m1 part. Simple. Okay, m into m1, and for all the spans, for CB, BD and DA, this into this plus this into this plus this into this. Okay, this is what we have done over here. Okay, and we have simplified the x value and we have substituted the limits and we got dr1 is equals to minus 747.25 upon En. Okay, this is the value for displacement at redundant coordinate. Now flexibility matrix or flexibility coefficient formation. Now here just remember we are going to form a square matrix and a symmetrical matrix, that and just F11, okay, this is F12, this is F21 and F22. Okay, this type of matrix we are going to form, and the coefficient and these coefficients are symmetrical, and these cross coefficients may be positive, negative, or may be varying in the value. Okay, this is what I have told in the starting of the lecture. Now how to calculate the flexibility coefficient matrix or F11 value. It is calculated as m1 into m1, that is m1 square into dx upon En. Now what is m1 into m1? We are going to multiply this value with this value, okay, plus this value with again this value, m1 into m1, again m1 into m1, okay, like this. So we have done simply square. Okay, we have marked square over all the values and we have solved for F11. Okay, it is 53.65 upon EI. It will take some time, that's why it is for 10, it is asked for 10 marks. Okay, but practice makes man perfect. You have to solve thoroughly for getting all the answers. Then the also then the actual displacement at redundant is 0. Okay, now in the original diagram it is a simply supported diagram, and in the given part they have not mentioned any displacement. Okay, any displacement, so that's why displacement at the redundant point or at the redundant is 0. So dr1, sorry, di1, what is di1? It is the deformation in the indeterminate structure due to first redundant. If it has dr2, then it will be deformation in the indeterminate structure due to second redundant. Okay, so these are the so here it C point does not have any displacement, that's why di1 is equals to 0. Then we will form a flexibility equation. Why we have calculated only one F11 coefficient? Because we have only one redundant over here. Okay, we have only one redundant over here, that's why we have calculated only one flexibility matrix. If we have two unknowns or two redundants, then we can easily form the square matrix. Okay, Then what is the flexibility compatibility equation? It is di, that is deformation in the indeterminate structure, is equals to deformation in the released structure. We have released with the redundant. Okay, so that dr1, sorry, dr, so this release structure deformation into f. F is the flexibility coefficient, that is 53.65. Okay, this 53.65, and into r is the redundant, that is unknown value that we are supposed to find over here, that is r1. Okay, so by substituting di is equals to 0 and all other values, we will get the value of r1. Ei is constant, so we can substitute 1 over there, so we get the value r1 is equals to 13.93 kilonewton. Okay, so it will complete our one numerical by getting the unknown, that is getting the redundant values. Okay, and the last step is drawing the shear force and bending moment diagram. Here we are supposed to find the bending moment diagram. Okay, so by using principle of superposition, we will find the bending moment diagram. This 40 is PAB upon L, and this is WL square by 8. Okay, and we have calculated one, we have cut one section and we have calculated one movement over that point. Okay, you can calculate it over any point. Okay, so this is the bending moment diagram, and this will complete our one numerical and for 10 marks. Okay, it is very simple, very easy method, flexibility matrix method, and it very but it has a lot of calculations. Okay, it has calculations of integration, but if we have got enough practice, then it will save your time. Okay, thank you. If you have any doubts regarding this point or this unit or this numerical, then you are free to ask me. Okay, comment your name and roll number in the comment box. Thank you.